This is sections 8.4, trigonometric substitution. In these sections, we will learn another type of substitutions. Besides the U substitutions, we call the substitutions that we learned in Count 1. Now, before we get there, make sure that you review all the trig identities that we might need during these sections. Here's the double angle identities. The sine of 2 theta is 2 sine theta cosine theta. We also have sine squared and cosine squared. This is called the power reducing identities. Okay, so sine squared is half, 1 minus cosine 2 theta, and cosine squared is half times 1 plus cosine 2 theta. You also want to review the integration rules. Okay, so we have lots of them. Here's a 2.1 here. The antiderivative problem for u is natural log of u. And the one that's becoming very common is the secant theta. The antiderivative secant is natural log secant plus tangent. All right, so then if you look at the two examples here, 2x over root x squared plus 4 versus 2x squared over root x squared plus 4. Now they look very similar. This one is square and this one without, but again techniques are very different. If you look at the first one, so what I'm going to do. So remember, when you dealing with the integrals, one thing you could do is simplify using the algebra simplifications, but in this case, there's nothing we can do. We cannot simplify. So we're going to use a substitution. Now, when you use substitutions, or when should we use substitutions? If you look at this carefully, I know we've got to use substitutions because in order to use substitution, you need to have a u and a u prime. So you must have a part, okay, a part called u, and then the other part is u prime in the integral. So when you see the x squared plus 4 and 2x, that one I know for sure. You can see the part right here. If you call that is u, all right, u, then you see that the derivative is 2x dx, and that is here. See the 2x? So that's how I recognize this could be done using substitutions. Okay, so I'm not going to finish that, but you see that this become a u. So when you change variables, then you have the square root of a u's here, right? 2x dx, the 2x dx becomes a du. So I'm going to write one here and that's du, and then you can integrate. Okay, or write this as u to negative half. Now versus the other problem here, notice that you have x squared plus 4 and then there's x squared in the top instead. Well, the thing would be different. You cannot use the substitutions in this case. Or sometime we can, but it's going to take a lot of work because you have extra x at the top. So what do we do? In these sections, we're going to use the technique here called the trig substitutions. And the idea is when you have the integral like this, you know what bothers us the most? The square root. Because of square roots here, that kind of make things hard to do. And so the idea is we want to use some techniques or some way to do so we can somehow simplify and get rid of the square root. Okay, so to do so, we're going to use the idea of trig identities. So if you think about this, if what's inside here is perfect square, then it's perfect, right? Perfect square is perfect. So what I want is to use some identities where I want x be something. Okay, so you see it's a bit different, or actually very different. Instead of you let the new variable u be a quantity in terms of x, we let x be a quantity, okay, x be something that is in terms of a different variable, okay. In this case, particularly, I want x to be 2 tangents theta. So you're going to have x is 2 tangent theta. Right, so you wonder why we have that. Let me show you why it works first, and then explain to you why we choose 2 tangent theta. So what happened is they want to turn the x into a trig function, 2 tangents. So what happens is inside, if you look what's inside now, okay, so the bottom is what? Square root of x squared plus 4, just work on the bottom only. Then what is this? Plus 4. Again, the x is 2 tangent. 2 tangent theta. And 2 tangent is equal to what? 4 tangent. Right, you see that's 4 tangent square. And then if I take out the 4, then I have a tangent square theta plus 1. Okay. Now, if you forget, so these are the identities that you might want to recall. The tangent square of theta plus 1 equal, that is the secant square. Okay. Remember what else you have? The sine square, right? Plus the cosine square is equal to 1. So the one that we're using here is actually secant square, right? Tangent square plus 1 is secant square. And you can see that becomes square root of 4. And tangent square plus 1 is secant square. You see now we have the perfect square inside the root. Square root of 4 is 2. Square root of cosine of secant square, secant square, is secant, actually the absolute values of secant theta. Okay, square root of square is absolute values. And unless we know secant theta is positive, we can drop the absolute value bar. So that's what we use here. Okay. Now, again, the idea is we want x be some trig function so that when you simplify, the identities could be applied to turn into a perfect square. Okay. Now, how do I know we're going to use this 2 tangent? Well, actually, because you see that the x there square plus constant, I'm thinking that it's going to be this one we use tangent square plus 1. But because if you put just the tangent, then you have tangent square plus 4, so it doesn't have the form that we need. So I need an extra 2, the factor 2 there, so that it makes 4 tangent square, and you take out the 4, you get tangent square plus 1. Okay, so here is actually the method 1. We're going to focus on method 1 actually for all of these problems. When you have the square root, okay, where you have the form, the one that we have actually square root of a squared plus x squared, then you let x be a time tangent. A time tangent. Then I also define the theta as between negative pi half to pi half. This quantity right here, would actually guarantee the secant come out to be positive. That way you don't need absolute value bar, you can easily integrate, right? You don't have the absolute value bar if you know it's positive. Likewise, when you see square root of a squared minus x squared, you will use x be a times sine theta. Again, the condition here between negative pi half and pi half to guarantee the cosine. I can simplify. If you look at what we have here, so let's say here's square root a squared minus x squared, right? If you let x be a sine, put in a sine, right? That a, so you're gonna have a squared sine square. So they have a squared in common. Take the a squared out. 1 minus x sine square, right? And 1 minus sine square. Square root a square is a. 1 minus sine square cosine square. And square root of cosine square is absolute of cosine. Cosine theta there. Now, because theta between negative pi half and pi half, this will help you rewrite this as just a time cosine of theta without the absolute values. Okay, so I hope you see the point. That's what I'm going to do. All right. So if you look at some of the examples here, I have lots of them. Actually, look at number 1. Right, so number 1, we have the integral of dx over the square root of 4 plus x squared. Now, normally that's what you would see in the textbook, the way the integral is written. But I always hate that writing. Is that the same as 1 over square root of 4 plus x squared dx? Okay, so I want a dx in the back instead of on top. So that way you can see the function clearly. The integrand is 1 over root 4 plus x squared. Now, so that's fall into the case 2 here, right? A squared plus x squared. The a's in this case is 2. So what you want to do is notice that I'm using substitution, but instead letting u equal, I'll let x, so this variable equal what? 2 tangent. A is 2. So in this case, A is 2. 2 tangent of theta. Now, don't forget, again, when changing variables, everything needs to change. Every x you've seen would become a theta this time, okay? So if you do the change of variables, then that will become integral, right? 1 over 1 root of 1 plus, again, your x is 2 tangent there. 2 tangent. Okay. Now, the most common mistake is you either forget your dx or you don't change the variable here. This is dx, that's the derivative of x. So what you have to do here is after you let x be, you always need to take a derivative of that substitution. So what's dx? Dx is 2 times derivative tangent is secant square. Right, derivative tangent is secant square. So don't forget that your dx is 2 times secant square. Okay, 2 times secant square. Okay, so don't forget that. Then what we do is we have Now a new variable in terms of data, although I think we can simplify a lot. Can we? Let's put this back on the top, 2 secant squared times that to be. So you have the integral, that's 2 secant squared. Okay, that's 2 secant squared. The denominators, we have what? 1 plus, sorry, it's not 1 here, my bad, it's the 4. So it will be square root of 4 plus 4 tangent square. So I can take out the 4. See that? 4 plus 4 tangent square, take out the 4, it becomes 1 plus tangent square. Okay, so from here, this become square root of 4 is 2. And then you have 1 plus tangent square. What's 1 plus tangent square? 1 plus tangent square we did up here. See 1 plus tangent square is secant square. So that becomes secant square. Okay, so that would be integral. You have 2 secant square on the top. That is 2 square root of secant square is secant. Now again, we're supposed to have absolute values, but when we let x be this, I think it should have a condition here for the theta. You want the theta to be between negative pi half and pi half. So that is the first and fourth quadrant. First and fourth quadrant. So that means the cosine be positive or secant is positive. All right, so from here, you can see there's some cancellation here, and then 1 secant it's got canceled. And we're left with just secant theta. Okay, so a review of here, the entire derivative secant is natural log. It's a natural log of natural log of absolute of secant theta plus tangent theta plus c. Notice that we are not done yet, even though I integrate this, right? So I integrate the secant, it's natural log secant plus tangent. But don't forget that the secant theta, tangent theta is in terms of the new variable. We need to change it back to the variable x, right? That's called back substitution. Well, we can always look at the relationship between the x and theta. You see how they're related? We divide by 2 on both sides, then we have x over 2 is tangent theta. So you see that the tangent theta, that is x over 2. X over 2. Now, what's secant? Well, from here, we're going to draw, we call it drawing the right triangles techniques. So let me draw the right triangle. Okay. and this is your theta. Now, I'm constructing this right triangle, satisfying this trig ratio. You see, tangent is x over 2, right? What's x? What's tangent? Tangent, we know it's opposite side over adjacent side. So the opposite sides of theta is this. So the opposite side in this case x. The adjacent is hypotenuse, right? X over 2, opposite over adjacent. So x is opposite, 2 is adjacent sides. Okay. Now, then once you have this, I can figure out the trig functions here to turn into the the x, right? So what's secant theta? Well, secant of theta is this the reciprocal of cosine. Cosine is adjacent over hypotenuse. So the secant is hypotenuse over adjacent side. Hypotenuse, what's hypotenuse? Hypotenuse is this length. Well, so this is x, this is 2. Can you figure out the length of hypotenuse? Yes. Remember the Pythagorean theorems, x squared r2 squared plus x squared equal to whatever this hypotenuse square, right? So the hypotenuse, if you take root on both sides, then your hypotenuse will be square root of 4 plus x squared. And now hypotenuse is square root of 4 plus x squared over adjacent side is 2. So your secant theta is square root of 4 plus x squared equal 2. Right? So that equal to natural log of plus constant. All right. So that finished the answer. Problem number 1 using the trig sub. Okay. All right. You can see the problem is a bit long, but you need to understand the concept here. All right. So you let x be one of these 3 choices. After you substitute in, simplify, you should get rid of the root, integrate from there, and then there's back substitutions where you need to construct the right triangles. Okay. Now let's look at number 2. Dx over root x squared minus 16. Okay. Now for number 2, you can see the writing here with dx at the top, which is never my favorite. It's the same as 1 over square root of x squared minus 16 dx. Okay. Now, what choices do we have? See, that one's x squared minus 4 squared, x squared minus 4 squared. So we got 4. X squared minus 4 squared. So we let x be a times secant. So that means we will let x be a is 4 times secant theta. Okay. Don't forget that once you're done, you start substitution. Don't forget to take a derivative immediately before you forget. So derivative secant. What derivative secant is secant times tangent. Okay. Now that will help us simplify it. This quantity right? So this quantity will become integral of 1 over square root of, plug in 4 secant theta squared. Now skip step here, we plug 4 secant theta in, that becomes 16 secant squared minus 16. Okay, and then from here, I can simplify. That's 1 over, you take the 16 out, you have 16 times secant square theta minus 1. And you see, I almost forget one important part is the dx. You see this dx. So I have, I'm going to put it on the top because before secant square theta. No, there's no square. Okay, that's for secant times tangent theta d theta. Okay, d theta. All right, so here again, it's actually 4 secant theta tangent theta. Okay, and then what we have, this become integral of, as they have 4 secant theta tangent theta d theta. Square root of 16 now is 4. Then here's square root of secant square minus 1. Here it is again. I'm using this trig identities, but it's be a little bit different, right? If you subtract 1 on both sides, then you have secant square minus 1. That's the same as tangent square. So you see that I have secant square minus 1. Secant square minus 1 is that one. It's tangent square. We're using the identities there. Now, from here, you can simplify a lot more. You see that the 4 and 4 cancel. This is tangent square with the tangent, so you cancel one of them. Then what do I have? Well, I can have nothing left, right? So that one and that one, we are left with secant theta. Secant theta there. So can we integrate after all this hard work? We are taking the entire derivative secant directly. Well, we have the formula for that. It's a natural log of secant theta plus tangent theta d theta. Okay, you see that's the same common secant there. All right, so we get to this point. What's do after we integrate? We do the substitute back. When you would talk about a substitute back, you're using the regional relationships between x and theta. So divided by 4, you have x over 4 times equal x over 4 equals secant theta. You see that one. That is x over 4. Okay, x over 4. Let's still have natural log. I think that's a plus c. All right, so we've done that, except one small thing, tangent. What's tangent? Well, again, from here, I can construct the right triangle satisfying this trig ratio. So what's secant again? Secant is tangent, hypotenuse. That is hypotenuse over, remember cosine is adjacent over hypotenuse, so this is reciprocal. Hypotenuse over adjacent side. So if that's the angle theta with adjacent side equals 4, the hypotenuse is x, and xe is in 4 there. Now to solve for the remaining side, you use the trig identity, using Pythagoras theorem again. It'll be x squared minus 4 squared, or 16. So you have the tangent is square root of x squared minus 16 over 4, right? Hypotenuse, sorry, opposite. Tangent is opposite over adjacent. Opposite over adjacent, yes. Okay. So that finished the problem number 2. Let me rewrite it and kind of box this. So that's natural log of x over 4 plus square root of x squared minus 16 over 4 plus c. Okay. Now, one thing you should observe carefully for these two problems. Notice your answer is 4, same denominator. I think the same is 2. And these 2 come from the 2 at the beginning, and that's 4 also come from the 4 beginning. Right? So just kind of the information here for you to check. So if you see this one is 4 squared, you don't see it 4 on the bottom, you know it's wrong. Okay, and also you see the square root at the beginning, see, now become the end of solutions. See that one? Now you see root 4 plus x squared and root 4 plus x squared. So these are things you remember, watch out, make sure that the answer comes out to be correct. Okay, so that's 1 and 2. And then the rest we will do the same. Let me do those in the next video.